All right, lesson 5.2, structural analysis, trusses. The objectives for this lesson: define a simple truss, calculate the forces in truss members using the method of joints, identify zero force members, and calculate the forces in truss members using the method of sections. Trusses, you see them up here. These are actually called steel joist. They are a type of truss. They are commonly used to support roofs. That's one of the many applications of trusses. For a given truss geometry and load, how can you determine the forces in the truss members to be able to select their sizes? Okay, so what I mean is if you've got this truss over here, somebody's got to say how deep it is and how big the member along the top here, which we call the top chord, by the way. That's kind of beyond this course, but it's good to throw out at parties when you're talking to people. The bottom one down here, the bottom chord, and these diagonals and verticals, web members, another cool word we have for them. Those are all parts of that truss, and somebody's got to figure out how big they are and what they're made out of. These trusses here look quite a bit different than this big truss back here, which is part of the lateral force resisting system for this building, like against wind and seismic, where these are just holding up the roof itself. So the moral of the story is somebody's got to be able to figure out, what the forces are and then size the members accordingly. Now, in statics, we are not sizing members. That's a strength of materials concept. But I tell all of my students that really, if you go to strength of materials, over half of that class is actually solving a statics problem. So when you go to design a member and figure out, what size member goes in here, that actual part is actually pretty easy. It's actually the statics of it that's the hard part, finding the forces in the truss members. So getting this down now is really important for moving forward. So other applications of trusses, cranes, airplanes, bridges, robotic arms, satellite, spacecraft, you name it, their trusses are everywhere. Wherever you see triangles, those are trusses. They allow for a design that is relatively lightweight and simple to build and maintain. They're fairly clean structures. They are very strong for the amount of weight required of them, and that's why you see them so much in like I was saying, bridges, any kind of long span situation like this tower crane up here. This is going quite a ways. It is made up of a bunch of truss elements so that it's not so heavy and still gets the job done. All right, so what is a truss? A truss is a type of structure composed of slender members joined together at their endpoints. And they're all always connected together with frictionless pins. So everywhere you look at each end of every single member, there's a frictionless pin holding all of them together, which means no moment gets resisted across those joints. And also, all loads must be applied at the joints, which are also often called nodes or panel points for trusses. You never load it along the member's length. And so if we make those assumptions, okay, that it's slender members joined together at their endpoints and that they're connected with frictionless pins and that they're only loaded at the panel points, basically those assumptions allow for a great simplification in our analysis. So trusses don't really actually exist, I hate to break it to you, because, first off, frictionless pins, I mean, come on, there's no such thing. Every pin is friction full to some degree. But, how can they be reasonably assumed to be frictionless? Also, what about, it says here that the loads must be applied at the joints and never along the member's length. Well, what about the weights of these members? Aren't they applied along their length? Don't these members want to sag to their own weight? As long as they're fairly lightweight, that's fine. And trusses usually have a order of magnitude or more higher capacity compared to the weights of their own members. So it's usually a decent assumption. But once we make these assumptions and we can reasonably apply them to a structure, we can say that it's a truss. Okay. The other thing that is big with trusses here is that they are always triangular elements. Always triangles in a simple truss. Okay, and so whenever you have all of these things happen, you get that very rigid, very easy to analyze system that we call a truss. Okay, and a simple truss is a planar truss or 2D truss, which begins with a triangular element. So maybe you have, 3 members, right? And you expand them by adding 2 members in a joint. So you're always just adding 2 members in a joint. So you're always getting triangles. Always, always, always triangles in a simple truss. And there are complex trusses that are like multiple simple trusses together. And in some cases, you can get away with not having a perfect triangle in every single spot. But in general, triangles, you should think trusses are triangles. It's the axial stiffness of these members that are causing them to be so good, and that's the whole point here. We're going to end up having axial tension or compression, right? 2 force members, so we're going to have axial tension and compression. It's these tensions and compressions that are in these members, and they're acting in the X and the Y because we always have triangles, right? So those are what are causing the rigidity of the system, what makes it such a good system. Okay. For these trusses, the number of members, M, and the number of joints, J, are related by the equation M is equal to 2J minus 3. So that's just always going to be true for a simple truss. When designing the members and joints of a truss, first it is necessary to determine the forces in each truss member. Meaning if you're going to size them, how big are the members? Again, that's not a statics problem, that's a strength of materials problem. But the point of this statement is saying that first off, we need to do the statics. We've got to find the statics out so that we can then size them. And so analyzing a truss is finding all of those internal tensions and compressions in all of the members. And like I said before, the weight of the truss and other things like that are often neglected or, maybe dealt with in various other ways. Even if you have a fairly heavy truss, what you can do is assume that the weights are acting only at the end point so that you're not putting any bending or moment into those members themselves, that it's just 2 force members everywhere you look. And by and large, that's a perfectly good simplification, and trusses are designed like this all the time. Trusses are everywhere you look, okay? Not just in bridges and in space stations, like I said before. They're absolutely everywhere. They're in your car. They are in your house. They are in every piece of machinery pretty much out there. They are all over the place because they're so lightweight. They are great ways to make very stiff elements. All right, so there's going to be a couple of ways that we analyze these things. And we're going to go through the method of joints and the method of sections, which are 2 methods of analyzing trusses. And the fun part about this is, and it's a lot of fun, is that you actually already know them. The method of joints is basically a equilibrium of a rigid particle, and the method of sections is equilibrium of a rigid body. Okay, but they have specific applications to trusses, and we like to give things fancy names so that, again, you can talk about them and to people that might not understand, and you sound smarter. So that's really what this is all about. We've got the method of joints here, and in the method of joints, we've got this simple truss here. It's got a pin support here, a roller, and it's just one triangle. It's about as simple of a truss as you can get. To analyze this, what we're going to do in method of joints is draw a free body diagram of just one joint. And if you think about it, all the members go towards that joint, and they all, converge on that joint. So all of the forces, if you look at a free body diagram of B, for instance, they are all concurrent forces. So this is equilibrium of a particle. And that means you have two equations of equilibrium, sum of forces in the x and sum of forces in the y, for a 2D planar truss using the method of joints. If you had 3D truss, we're not really going to get into that too much in here, but then you would have for a particle sum of forces in the x, y, and z. But for the most part, we're going to have sum of forces in the x and y. Again, a particle problem. Moment equations have no business here because there is no moment caused by any of these forces about point B. So you're just out of luck. If you're going to, you can try to build a moment equation, I guess, but you know, all the moment is going to be zero because all of these distances are zero because all these forces are acting through, their lines of action are acting through point B. So that's the method of joints. How do you do that? Well, you solve for the trusses reactions first using the overall structure. Sometimes you can get away without this step, but it's usually required. Meaning, when in doubt, and unless you have good, a good hunch to think otherwise, solve for the reactions first. You got to do it on the overall structure because as soon as you start cutting free body diagrams, you're releasing those, you're making those internal forces unknowns, and that's just going to make more unknowns for you. So you want to solve for the reactions on the overall structure before you get started cutting free bodies. Okay, so if you're going to draw a free body diagram of a joint and there's a reaction vector there, you need to know that reaction vector at that joint before you draw that free body diagram of that joint. Okay. Once you've got that, then draw the free body diagram of the joint. And that joint, in general, your joint should only have one or two unknowns because you have two equations of equilibrium, right? You have sum of forces in the x and sum of forces in the y. And so if you have three unknown members framing in, you're going to be out of luck. You might stick a pin in it and come back to it later because maybe you'll go to a different joint, find out one of the forces that are happening at that joint that will inform you about the other joint. Because in method of joints, we're going joint to joint to joint to joint to joint. It's like connected dots. Like if you've been to Chuck E. Cheese and while you're waiting for your pizza to come, you've got your little placemat there and there's a bunch of dots and it says 1, 2, 3, 4, 5, 6, and it goes all the way like to 150. And by the time you connected all the dots, you actually knew it was going to be a big mouse's head, right? That is what we're doing with the method of joints. You go from one dot. You go from one dot to the next dot, to the next dot, to the next dot. You are like a human computer. And in each case, again, you are going to sum forces in the x and y, and then you're going to write those numbers when you find new answers on your free body diagrams, because then you're going to go to the next joint and take those values that you learned at the previous joint and apply them to the new joint. And if you point them away from the joint, on your free body diagrams, and you solve for them and they are positive, it means two things. It means, first off, you made the right assumption for direction, so yay for you. But secondly, you also know that positive means tension. And tension is when a member is pulling on a joint, right? I mean, a member in tension is being stretched. So the joints are pulling the member longer, and conversely, since we're thinking about it as a method of joints approach, we're drawing free body diagrams with the joints, the members are pulling on the joints, okay? If you tie a rope against the wall and you pull on the rope, isn't the rope wanting to pull the wall with it? That's what we're thinking about here, right? And, if you're pulling on a rope that's tied to the wall, and we were just talking about the wall, but what's the rope doing to your hand? It's actually wanting to pull your hand back too, right? They're always wanting to pull away from their joints when it's in tension, and the vectors always want to be pointing towards the joints in compression. And so the point is here is if you solve for a force at one joint and it's in tension, when you go to the other end of that same member, the arrow flips direction. If it were tension, it would have been pointing away from joint A, for instance, and the other end of member AB is over at B. Well, guess what? The tension force at B of that member will be pointing away from B. So when you go to what I like to say is the quote-unquote other side of the free body, which just means the other end. Other is a very vague term because you're going to be drawing lots of free bodies, and, it is kind of vague. But when you go to that other side, the arrows flip direction. You'll see that time and time again in statics, especially in trusses here and now.